Well, I just picked up this new toy recently on eBay. It's Agilent E4421B signal generator. It goes up to 3 gigahertz and it does all the sort of modulation and all the other bells and whistles you'd expect from an RF gen. So before we stick it on the shelf, I think we need to take it apart and see what's inside it. We've got it hooked up to the RF Voodoo spectrum analyzer, showing a nice spike at 3 gigahertz there. Right, not surprisingly, with most RF equipment, there's heavy shielding. So there's this shield on here before you get at any of even the non-RF bits, and there's a second card cage over to the right here. There's got the RF boards, which are all in their own internal self-shielded castings. These just done plug-in boards, but with a heavy cast shield on them. Fortunately, they give you a little key showing you which things plug in where. And there's a bunch of slots here. These are all unpopulated, but there's various options like the various digital modulation options. There's an arbitrary waveform generator option, a few other things that will plug in here. So this is the main digital and baseband processing board. Backup battery there. These are connectors which probably go to optional rear sockets. Some of the options, maybe some of the options that plug in here. Yeah, there's a few odd connectors here which may be for optional rear panel sockets or for test or something. There's analog devices DSP. I'd imagine that's probably to do with the modulation side of things. I'm guessing that'll be the main processor there, which is 68332, so it's a 68,000 series. Another big connector there. I'm not quite sure what that would be. Perhaps it's a memory upgrade option or just some other plug-in option. Obviously RF is used in all sorts of different applications, so there's lots of different options on this thing for different fields, whether it's cellular or different types of modem protocols. So there's loads and loads of different versions of this with various different plug-in boards and software options. There's down here, this is the input from the power supply, so we've got all the voltage regulators here. There's going to be lots of different power supply rails in a thing like this. So a little bunch of LEDs there. I'm guessing that's maybe one LED for each power rail. Yeah, in fact you can see next to it, it actually shows the voltage next to each one. There's yeah, plus 5.2, plus 12, plus 32, minus 15, plus 15, minus 5.2, plus minus 5.2 I think is used for ECL, high speed logic, from memory. So about 10 different supply rails there. A couple of PLC EEPROMs, some RAM, flash memory there. I'm quite sure, I wonder if maybe the EEPROMs have got some sort of bootloader or something in them and the flash memory's got the main program code. I'm not quite sure why you'd have both EEPROMs and flash in there. A couple of little bodge wires. A non-populated connector there. The front, again, sort of the other side is some shielding. You've got the display. That'll be the inverter for the backlight. This is a cold cathode fluorescent backlight. And there's a PCB on the back here which is just going to have the encoder and the buttons. I'm not going to bother taking that apart, there won't be anything interesting in there. There's just a ribbon cable that comes from that PCB onto the main board. And a couple of fans. This thing was absolutely caked in dust when I got it. It's obviously been running for quite a long time. There's no filters on these fans, but they do have quite a nice fairly clear air path through them, so that it got a lot of air flowing through it, and the thing had tons and tons of dust that I had to clear out. And just stuck on the end of the board here is the GPIB interface, and over here there's this rather awkward to get at can, inside which there's the power supply. This is a pretty bog standard switch mode power supply, nothing particularly exciting here. Interesting little detail on there, it's saying it's got Agilent and Hewlett Packard, so I suspect maybe they just added the Agilent to the artwork. See, look, the typeface of the Hewlett Packard matches the part number stuff, so I suspect they just sort of slapped that Agilent on at some point during the production process when they changed the name of the company. And it's got the outputs, 150 watt outputs, 5.2 volts, 12 minus 12, another 12 volts, 15 volt standby, made in Korea, so this may well have been made by a third party and just supplied as a sort of custom build to Agilent. It's quite common for power supplies to be made by power supply specialists. If you're building sort of exotic RF signal generators, it isn't really a very good use of your time to reinvent the wheel designing power supply for it. Little detail here, as well as the mains filter, they've actually got these ferrite sleeves across the leads as well. So just add a bit of extra filtering to it at the high frequencies. Right, this is the synthesizer board. Left all the screws in just in case they're different lengths. I don't want to risk getting those mixed up. And you can see lots of interesting RF goodness here. All these sections are in separate shielded enclosures. Look on the inside of the cover, you can see there's cast sections, and it's got this springy gasket material in there, so that when it's pressed down it's pressing continuously over the whole board to minimise the inductance, so to get the maximum shielding of each section from its neighbour. There's I think it's a rubber core or something in the middle of that as well. So you can see there's lots of different sections on here. This is clearly the output because that's the only coax socket on the board, and you've got all these different sections and they're actually marked with different frequency bands. So I'm not quite sure whether this is the oscillator and these are controlling the oscillation frequency. Don't really know enough about how this stuff works. I couldn't immediately see anything resembling a service manual online. But you've got these different sections. You can see on the back here there's also the same thing that's partitioned on both sides of the board. Not a great deal on the back, just some passives. But for example, if you look here, there's a whole chain of parts of sort of 250 to 396 megahertz, 396 to 620, 620 to 1000, and there's all these other bits around here have also got their own frequency ranges. Here for example, 1.6 to 2.8 gig, 1.26 to 1.6 gig. So there's different sections covering different frequency ranges, and there seems to be diodes sort of on the this light is all sort of clearly going down towards here to the output, but there's a lot of diodes here, which I'm guessing is just for switching, so they adjust the DC bias on the diodes to switch different sections in and out. So for example here there's a 2.52 gig, 2.52 to 3.2 gigahertz and 3.2 to 4 gigahertz. And interesting, this unit comes in 2, 3 and 4 gigahertz versions, but obviously a lot of the hardware is the same, so although this is only a 3 gig version, it's got the components for the 3.2 to 4 gig on this board. I don't know which other boards are involved, and I suspect it's probably not trivial just to sort of tweak something and upgrade it. If nothing else, the calibration will almost certainly only be done for the range, that particular model. And you can see there's all sorts of weird, when you're doing RF stuff, you don't just lay everything out in nice right angles and nice rectangular arrays. It's very much sort of the layout's dictated by the stray inductances, and so you've got this sort of tracks meandering around components at all sorts of weird wacky angles, lots and lots of wires stitching through the board to minimise the inductance of the ground plane, because at these frequencies, a small length of track has significant inductance, so there's lots and lots and lots of these wires just stitching both sides of the board together, and they probably go through the inner layers as well. And over here in the middle this is obviously all the digital control stuff. There's a D to A converter here, there's a few relays dotted around which would be for sort of very signal switching. There's an HP custom mark chip, whether that's a custom chip or a custom marking, I don't know. That says FRAC M, which is probably a reference to the synthesizer. There's a technical fractional N synthesis, which allows a wide frequency range without having to have ridiculously high clock rates. There's some very high precision, some 0.01% 10k resistors down here. There's a section over here which is marked VCO. Now I can't see that this is generating sort of 3 gigahertz and then sort of taking it all the way to this other side of the board, so maybe that's a lower frequency VCO that's then multiplied or something. But some obviously RF type transistor packages, these little circular packages, are fairly typical for very high frequency stuff, because they're the other package sits on the same plane, so you don't have the inductance of leads curling round. There's a high-speed ultra-low noise op amp there, probably to do with the modulation, I'd imagine. It's a bit hard to really see the flow of signals around here, and these obviously parts seem to flow downwards sort of towards this area, but this is probably a link across this row of capacitors, which is probably filtering a transition from this digital section to the RF section. These are all analog switches. Quite a few sort of power transistors here. I don't know whether those are for actually dissipating serious power, maybe for thermal stability or something. It says synth supply, so maybe this is some ultra low noise power supplies. So obviously any noise on the power supply, if you've got a voltage controlled oscillator, that's going to be very sensitive to noise on the power supply, so this may or just be producing like super clean power supplies for all the analog RF stuff. And so on the back it's really just a big bunch of various passives. There's nothing particularly interesting there. That these capacitors here are obviously part of the filter that's made up on these inductors over here. There's a legend here that says first doubler, so that's probably a frequency multiplier of some sort. What an interesting chip here. This is an ATsemi SCX6206, which is actually a gate array. It's a sort of, I think it's a sort of semi-custom ASIC device. I found the data sheet's back to 1985, so it's a pretty old device. I'm guessing this is probably a fairly old design. Although it's sort of certainly from the HP rather than Agilent days, I would have thought, to use a chip that old. Right, this is the output board, so this will be the amplifier. There's a direct connection between the synthesizer board to this socket here, and you can see I was actually expecting, with all these blank areas, I was expecting to see some parts on the bottom side, but actually there isn't any. There's this sort of layer of wires, so there's obviously a transmission line through the inner layers of the PCB going up here. Then we've got some of these weird fan-shaped things, similar to what we saw on the Anritsu spectrum analyzer teardown. Again, these will be sort of filters of some sort. And again, we've also got these sort of chains of inductors with capacitors on the other side that we saw on the synthesizer board as well. And there's another one of these ATsemi gate array chips. Some interesting sort of ceramic packaged devices here. These will be sort of super high frequency amplifiers or buffers or something. There's a little sort of can filter that's got 2 MHz written on it. I don't know if that's maybe to do with the modulation. So because this is controlling the output, I would expect this board probably also handles amplitude modulation. There's a couple of 8-channel D to A converters. There's one over here and one here. So I would imagine that this is perhaps in charge of the amplitude modulation side of things. Then there's this is clearly the final output device. This goes to this connector here that goes into the output attenuator block, and there's this funky looking Agilent custom thing, and they actually helpfully tell you which order to unscrew things in, because obviously this thing is sort of basically floating on the board, so this gets bolted to the case last to avoid putting stresses on the pins where it's all screwed together, and when it heats up, so it tells you which order to do and undo the screws, which is nice. There's a couple of HC595s, which I'm sure will just be I/O expanders. There's quite a lot of big caps and inductors. I'm sure this will just be producing a nice clean smooth power supply for everything. And that's about it. A couple of fairly big polypropylene capacitors there. Maybe that's to do with the amplitude modulation coupling or something. That's about it. They're surprisingly little on the bottom side. Just a few random passives, some caps on the power supply, a little bit more Voodoo trackery down there, and a sort of completely unused section. Right, this is the reference board. You can see there's a hole in the shielding can for the oscillator. They obviously couldn't get one small enough to fit. I'm not sure if this is a TCXO temperature compensated oscillator or an ovened oscillator. According to the spec sheet, there's 2 versions. The standard version, this is 1 ppm accuracy, and there's another version with better than 0.1 ppm, so I'm guessing the 0.1 ppm uses the oven oscillator, and this may well be just a normal temperature compensated oscillator. It's all sort of relatively sort of standard stuff in here, not too much RF Voodoo. So we've got the actual oscillator here. I'm quite sure if that's some sort of yeah, it could be some sort of dielectric resonator oscillator or something. There's an RF transistor near it, so perhaps that's a high frequency reference that they're phase locking off of this this reference here perhaps. Another one of these SCX 6206 gate arrays. They seem to be using those on most of the boards. A few HC595s, which will probably be for just I/O control. Again, lots of caps here, which will be power supply. A whole huge bunch of analog stuff over here. And there's lots of D to A converters all over this bit. Not quite sure what this bit will be doing. No, I mean nothing at all on the bottom side of this board. This is relatively low frequency. There's no coax outputs on this either, so this is going to be relatively sort of sensible frequency stuff on this board. One little detail you can see on here, there's actually a few different footprints shown for different options, so it may be the alternate parts for different accuracy specs or different manufacturers of the oscillator. Now if we look inside this cage, you can see around all the connectors they've got sort of shielding fingers to get good sort of shielding integrity around each connector separately, so they're all shielded. You can see there's some traces here which have got wires sort of stitched either side, so they're all effectively producing internal shielding on the PCB. So the traces all run on the internal layers, and the ground plane either side and the stitching sort of covers it. And these are the connectors for the coax connectors on the PCBs, and there's a sort of airflow all the way through via this fan, sort of front to back. And the other side you can see these bits of hardline coax. This is the link from the synthesizer up to the output board. There's a few other bits here. There's this link. This is from the output into the output attenuator. This then runs to the main output socket. This one's got the output socket on the back panel, which is a non-standard option. It's normally on the front, so I'm sure there's a different version of this which actually goes up and across to the front panel. These, I'm not sure if these are actually sort of ferrites for common mode filtering, or I've actually seen these, they're just sort of like lumps of plastic to allow them to be clamped down, so I'm not actually sure if these are functional or mechanical parts here. Right, this is the output attenuator. This is probably one of the more critical parts of the system, because it needs to accurately produce the levels that you tell it to. So this is made, instead of the aluminium, it's got a very shiny finish. I don't know if it's maybe a nickel plate or something to get good surface conductivity. And there's this, I have no idea what's in here, whether this is some sort of funky semiconductor device or some ultra high frequency relays or something. I really don't know, and I'm definitely not going to go inside this. Sorry about that. I do actually want to have this thing still work. I'm not finished with it. And you can see actually underneath here there's actually some gasket material as well, some RF gasket, to make sure this is, because obviously this is probably one of the most critical parts, in that you've got the signal coming in here and it then sort of makes its way out here, but you can't have any crosstalk across here, because that, you know, you're attenuating potentially very large amounts of attenuation. So the output range of this thing is, I think, something like plus 10 to minus 130 something dB, so you've got potentially a massive difference. Okay, some of that signal level may be done before it gets here, but you've got, you know, a vast amount of attenuation, but accurate controlled attenuation at the low output settings. So the last thing you want is some power just to leak past the attenuator. There's a whole bunch of analog switches here and lots of these little filters, so I wonder if maybe this is some sort of, you know, high frequency analog switch type thing, and then these provide DC levels to switch different attenuation paths in and out to control the level. When I was playing around adjusting the level, I didn't hear any relay clicking, so I think it may well be some sort of semiconductor device. And so you can see that sort of vias are just stitched everywhere, and you can actually see there's actually a path either side of the signal path here. There's I'm assuming is an output relay here. That's probably just an on-off. So I wonder if it might be some sort of sampling thing to measure the SWR. Maybe here we've got perhaps some power monitoring and standing wave ratio monitoring, so it can detect overloads and badly connected loads, I would imagine. Not a great deal else in here. The connector obviously is just the control input, but this is probably one of the most critical and expensive pieces of this. I'd be very interested to know what's in there, but I'm not going to open it. And again, you can see this is another part where it's got the old Hewlett-Packard branding but an Agilent sticker on it, so this was obviously being made during the transition period between HP and Agilent. Well, I think this explains why there's so much dust in this thing. Apparently it's been running for 44,000 hours, which is about 5 years continuously. So obviously this was used in an environment where it was just run all day, every day, never switched off. As we look at the output on the scope, you can see we are getting some quite sort of smooth amplitude changes. There's a slight sort of clickiness occasionally, but there's no clicking or anything, so I think that attenuator module must be some Voodoo electronic attenuation system. Well, the one aspect of this thing I do actually have the ability to calibrate is the frequency. This is one of those eBay rubidium frequency standards, which is being used as a reference for my frequency counter. So I left this running for a couple of hours to stabilise and then adjusted it. There's actually a front panel adjustment for the trim on the oscillator, so that's within 0.02 ppm, which I think is perfectly okay. I was having a play around with the spectrum analyzer in this thing. I was just really looking to see sort of how low a signal we could get out of this and still be measurable by the analyzer. And so I sort of set it up with the 1 gig output, and this is sort of like fairly low down in the noise floor of the analyzer. But I then turned the RF off and noticed we're still getting a spike at 1 gigahertz. That's strange. So we should tweak the frequency a little bit, and looks like there's something somewhere giving us some 1 gigahertz that's being picked up with using fairly sort of standard RF cable. It's not super shielded thing. So I was sort of wondering what that might be. Let's turn the generator off, and I noticed the scope was on. That's got a sampling frequency without order, so if I turn the scope off, it's reduced it a bit. It looks like some of it was coming from the scope, but I think there's maybe still something coming from somewhere else. But there was definitely something. I have to turn it back on. Yeah, now it's started up. It's just seems to be a tiny little signal. There might be something coming from the PC as well. Okay, scope's now started up, and we're back up at about minus 120 dB. Turn it off. It is bouncing up and down a little bit, which suggests maybe there's some modulation or something on it, so it's not getting it on every sample. If I turn the scope off again, it disappears back down. Right, back to the generator. I just really wanted to look at how low this thing will actually go and still be resolvable. When we turn it down, it sort of gets hard to sort of pick out from the noise floor at about minus 130 dBm or so. Which, if you think of a normal sort of radio receiver, the sensitivity of that is typically in the sort of minus 90 to minus 100 dBm region. A really good one might be like minus 105 or something. So this is an extremely low level signal. And if you actually look at the range that this thing can do, this goes from I think the spec is plus 10 dBm. It will actually go higher, but if you look on the scope, it does start clipping above about 10 dBm. The range of minus 130, I think it's minus 136 or so is the minimum. Yeah, minus 136 up to plus 10. That's a range of about 10 to the 14 of the voltage output level, which is a truly staggering range. Now, if you're not familiar with dB, it can be hard to imagine the difference between the outputs, the output range of this thing, and in general, the ranges of signal levels used in RF. For example, the difference between the sensitivity of a receiver and the output of a transmitter. So here's a simple example. If we assume that the lowest output of this thing corresponds to 1 millimeter distance, then 0 dB corresponds to the distance from the Earth to the Sun.